Um, Good morning, and I would like to start my talk by thanking the organizer for organizing this conference and for the invitation to speak here. The title of my talk is K3, M24, and Holographic Moonshine. I think my talk is a little bit special because I feel I have to explain 2 of the 3 nouns of my title. But that's a nice illustration of the comment made by Sensen during his talk that, well, if you have a nice mathematical structure, and eventually it's going to find its place in string theory, and string theory is often also a great tool to study it. And in his case, it was the integrability, and in my case, it would be the moonshine. So let me start with actually introducing these nouns. So what is moonshine? So it started with this, with exactly this, staring at the J function. So the J function is the most natural object that is invariant under the torus mapping class group SL2Z. And if you stare long enough, and if you were John McKay, you might come up with the McKay equation, which says that 196,884 equals 196,883 plus 1. Okay, that's certainly true, but what is the significance? Well, the significance is that these numbers in red are actually also the dimensions of irreducible representations of the so-called monster group, which is the largest sporadic group. So it is as if there's something between the most natural modular function and the largest sporadic group going on that we don't understand why, because a priori they don't know each other. So more generally, the term moonshine refers to the phenomenon that the sporadic group and the modular objects are related in some mysterious ways. And so these are the 2 protagonists in this game, the sporadic group and modular objects. So let's start by introducing them. So what are sporadic groups? Well, they are simply just finite simple groups that don't come in infinite families. So to put it simply, they're just the misfits in finite simple groups. And there are 2 very famous such misfits among the 26. The first one is the monster, because it's the biggest. The number of its elements goes like 10 to the 54, which is a gigantic number. And the second one is the largest Mathieu group, M24, which will be our object here. And, well, it's famous also because it's the oldest. In fact, I just got an email from John McKay yesterday pointing out that I should have cited Frobenius for properties of M24. So it's from that time. So let's now talk a little bit more about M24, so which is who is our star in the story. So what is M24? First of all, the number 24 comes from the fact that it has a natural 24-dimensional representation. And on this representation, it acts as a subgroup of S24 that permutes 24 objects. And it also has another interesting property that it leaves a certain special 24-dimensional lattice invariant. And using this property, mathematicians have shown that all symmetries of K3 that preserves the hyperkähler structure have to actually sit in M23, which is a subgroup of M24. So this is the first hint that the Mathieu groups have something to do with K3 surfaces. And now the second object, the modular forms. So what are they? So Sergey has talked about it in his talk, so let's be brief. Basically, a modular form is a function defined on the upper half plane that transforms covariantly under a subgroup of SO2R. So instead of considering it as a function in the upper half plane, you can simply think about it as a function defined on the fundamental domain of your group, because its value on the rest of the upper half plane can be deduced by the transformation rules. And we also need a slightly more general concept, which is automorphic forms. So basically, it's the same thing, but you just replace upper half plane by something higher dimensional. So for our purpose, you can just think about it as the higher dimensional version of modular forms. And in physics, this automorphism usually reflects an underlying symmetry of the problem. With that said, it wouldn't surprise you that string theory is extremely good at producing such automorphic forms, because it has a lot of symmetries. And no matter whether it's a worldsheet symmetry or space-time TS-U dualities, once you have a symmetry, all symmetries have to be reflected in suitable partition functions. And the simplest example is the torus, is the 2D CFT partition function. Since we can think about it as coming from a torus worldsheet, it's usually invariant under the mapping class group SO to Z of the torus. So this property makes string theory a very good tool to study the Moonshine phenomenon, since the Moonshine is all about modular forms. So let's come back to the Monstrous Moonshine story. This phenomenon that we saw in the first transparency is partially explained by conformal field theory. And this goes like follows. So the claim is that this J function that is invariant under SO to Z can be thought of as a partition function of a chiral CFT with a monster symmetry. So since this is a symmetry of your problem, it won't surprise you that it's a symmetry of your Hilbert space. And if you compute the partition function, then the observation we just saw has to follow. So that's one explanation. And the mathematical proof actually used the elements of bosonic string theory. So the Moonshine conjecture was eventually proven by Borchert, which got him his Fields Medal, by introducing the concept of generalized cut-Moody algebras and considering the kind of lift of J of tau into an automorphic form. It doesn't matter if you don't know what these words are, because physically it's something familiar. This lift simply corresponds to considering the 26-dimensional bosonic string instead of just the 2-dimensional CFT. So to summarize, so this is the paradigm of Moonshine that we have seen before. An example of it is the Monstrous Moonshine that we just reviewed. So you start with the sporadic group, and all these boxes are what the mathematicians would write, but physically, this sporadic group will be the symmetry of your problem, and then you will have, for instance, a conformal field theory in 2 dimensions with this symmetry, and you can sort of lift it into a bosonic string, and its partition function will be given by a certain automorphic form with interesting symmetries, and its spectrum will actually be generated by an infinite dimensional algebra. So that's what I would call the physics of Moonshine that we know. So after this introduction on Moonshine, we can start to talk about the new story. So last year, these 3 authors made a striking observation on the BPS sector of the K3 supersymmetric sigma model. The observation is the following. If we, yes. If we look at the K3 elliptic genus, and we make this specific decomposition, which have the physical interpretation as counting the number of massive n equals 4 multiplets. We'll say more about that later. And so these 3 gentlemen then observed that these numbers are also the dimensions of irreducible representations of M24. So this should start ringing a bell. It sounds like Moonshine here. And so what is going on? This is extremely surprising because, well, I mean, all those numbers have been computed 20 years ago. And so it's extremely surprising that there's something hidden there that we don't understand. You can say, well, the staring took 20 years this time, so what's a big deal? But we really don't understand why. So eventually, the why question is what we want to answer. But before doing that, we want to answer some what questions. For instance, what precisely are we conjecturing? And in particular, what should be the Moonshine diagram? What should it look like in this case? What's the physics? And what are the consequences? Are they consistent with what we know? And relatedly, what are the evidences for such a M24 in the story? So that would be the topic of the first part of my talk. And I hope I'll get to the second part. The second part is, well, fortunately or unfortunately, along the way, we're actually confronted with an old puzzle that goes under the name Genus 0. And surprisingly, it seems that ADS-CFT will give us some hints about how to solve this puzzle. So that's what we call the holographic modularity of moonshines. That will be the topic of the second part of my talk. So now the first part, K3 and M24. So in order to tell you something about what we're conjecturing and what the physics is, let's start by recalling the knowledge we have on K3 compactified string theory. So let's start with where it got started, the K3 sigma model. So if we have a superconformal field theory in 2 dimensions with 2,2 supersymmetry, and the BPS states are counted by the so-called elliptic genus that is defined in this way. And you can think about it as a generalized version of the Witten index counting BPS states. But here we have 2 parameters, tau and z, because we want to keep track of the 2 quantum numbers L0 and J0 coming from the Virasoro algebra and the U1 current, R current of the problem. And as we have mentioned before, just by being simply a partition function of a CFT, it transforms under SO2Z nicely. Furthermore, we have more symmetries, which is called the spectral flow symmetry of the superconformal algebra, and that will give us actual conditions such that in the double expansion in Q and Y, the Fourier coefficients C will depend only on this very specific combination of the 2 integers, and that these properties give them the name, the Jacobi forms. But we're talking about K3. So far, we have used only 2,2 supersymmetry. But in K3, because it's hyperkiller, we actually have 4,4 supersymmetry, and we want to use it. So as we said before, this 4,4 supersymmetry has led to this specific decomposition here. And the most interesting part is this part that I extract here for you, down here. And it has an interpretation of counting the number of massive n equals 4 multiplets. And it also has the property, as I showed you earlier, that the Fourier coefficients look a lot like M24 representations. And modularity-wise, it is actually a modular form. As Sergey mentioned, it is just yet another type of modular forms with a slightly more complicated transformation property. That's all we need to know, but not as wild as the quantum modular forms that he mentioned. Okay, so so this is the sigma model. If we want to do, black holes in 4 dimensions, non-perturbative states in 4 dimensions, we want to compactify it further down. So let's look at actually type 2 string on K3 times T2. And this is a system that has been intensively studied in the past few years by many people, well, including myself. But let's just refer to the talks of Ashok in the previous couple of years for that, because I won't have time to explain that. And the motivation there is also pretty different. So for reasons I don't have time to explain, but is well understood by now, for this further compactification down to 4 dimensions by adding a torus can be achieved by so-called Borchers lifting the elliptic genus. with the same kind of portrait slip that we mentioned earlier. And what it means is simply that it's a sort of exponentiation. You turn a double infinite series in Q and Y, as seen in the elliptic genus, into an infinite product of this form. And then the Fourier coefficient will now become the exponent. And then you add one more parameters, P and Q. Now you have P and Q and Y. And the resulting automorphic forms from such a procedure a la Borcher's actually miraculously or not counts the quarter BPS states of the n equals 4, d equals 4 theory after compactifying down on K3 times T2. So what does it mean that it counts something? Well, in 4 dimensions, in this theory, a particle can have electric and magnetic charges. So let's call it Q and P. So we have 2 vectors. And the only physical invariants that you care about are the inner products of such 2 vectors. So there are 3 of them here. And for instance, if the charges Q and P got very large, then they actually form a black hole. And the black hole entropy is given by the log of this degeneracy D that you can extract from this automorphic form in this way. So that's very nice. And even nicer, this automorphic form actually defines for you an algebraic structure that underlies the quarter BPS spectrum. Okay, so these are the quarter BPS states. Since we have n equals 4, we also have half BPS states. So how about them? Not so surprisingly, the half BPS states are simpler to count simply because we have more supersymmetry. And actually, by using the heterotic type 2 duality, they are just counted by this famous 1 over eta to the 24, which is also the partition function if you just have 24 chiral bosons. And one immediate consequence of this is that, well, the half BPS state Hilbert space forms an M24 representation. Why is that? It's simply because, remember that M24 can be thought of as a S24, a subgroup of S24 permuting 24 bosons. So you immediately get this consequence that M24 maps a half BPS states to each other. And one thing that is very fun about n equals 4 theories is that the quarter BPS states have to know about half BPS states. They are not totally independent. And this is because, well, you can have the following situation, that you have a particle which preserves half of the supersymmetry in its isolation. And if you put another one of this similar sort, together they might form a bound state that together only preserves a quarter of the supersymmetries. And since they are quarter BPS, you have to find them in your spectrum. So indeed, if you look, they are present as an actual poles in the quarter BPS partition function. To be more specific, if you look at this dione counting automorphic form phi, and if you look at the poles, and in its residue, you find 2 copies of 1 over eta to the 24, counting the 2 half BPS states. So to summarize the physics of K3 compactified string theory that I talked about as the following diagram, we start with the K3 elliptic genus, and we compactify, or in other words, we lift, then we get the quarter BPS states in type 2 compactified on K3 times T2. And this dione counting automorphic form also defines for you an infinite dimensional algebra exactly of the same kind that Borcher's had. And it generates the quarter BPS spectrum. And in the other direction, if you want to study bound states, then you find them in the poles of the function, and you get the partition function of the half BPS states in the same 4-dimensional theory. And so from here, it should be clear what the Moonshine diagram should look like. Because we have all the structures ready, we just have to conjecture that there's an extra box, M24, which is a symmetry of all of these objects that were present there already. And the next step we want to do is to turn this diagram into equations, because we want to have some concrete equations that we can test. But before I write down some concrete conjectures, well, even before we do that, it's likely to be true, whatever I'm going to conjecture. Simply by the fact that we already know that this M24 is a symmetry of the half BPS states. So it won't be that shocking if it's also the symmetry of the quarter BPS states. And in this diagram and everywhere else, the dashed line will be conjectural, and all the solid lines in all colors are facts. Okay, so what exactly do we want to conjecture? Let's begin by this observation. Remember that the observation was that all these numbers are dimensions of representations of M24. So you might simply want to make the conjecture that this is true for all n, not just the first few terms that we have explicitly checked. This is a true conjecture. Unfortunately, it's also completely meaningless because, well, just imagine that you can always take a bunch of trivial representations, singlets, as many as you want, to make this true. So just like what Edward Witten has told us earlier in the week, we need more information about the underlying vector space and not just its dimension. So how do we get more information? Well, we can do that by twisting. Suppose you have some symmetry of your underlying your Hilbert space, and you can twist the partition function. In this way by an extra insertion. So you're computing the character instead of just the dimension of your representation. And it will give finer information about the underlying vector space. So a simple example will be if you have two-dimensional CFT. In that case, then the twisting can be achieved by changing the boundary conditions. And before, we have the group SO2Z being the invariance group simply because it doesn't change the torus. But now, an SO2Z transformation will, in general, change your boundary condition. So in this case, the twisted partition function will be invariant under a slightly different group than the original SO2Z. A familiar example is when you have supersymmetry in the game, and you have bosonic and fermionic representations. And in that case, you can compute the partition function. Alternatively, you can compute the index, which is, in this case, a special case of twisted partition functions. And the statement that your group has changed is simply the statement that you also have to preserve the spin structure, not just the torus itself. Okay, so with that in mind, let's twist our moonshine. So we can make the following conjecture instead. Okay, so we can now compute the twisted elliptic genus by inserting this twisting element in your trace over the Hilbert space. And as before, we extract the interesting part. We call it H sub G of tau. And the conjecture is for all elements of M24, sorry, this should be small letter. This Hg of tau should again have a modular behavior, but under a different group. We call it gamma sub G, and have the condition, and also satisfy the condition that these numbers, all these numbers, are given by characters of representations of M24. So these K sub n label different representations of M24. So as opposed to the previous version, this is clearly a non-trivial statement that we can test. And now I can tell you what the status is for this conjecture. Well, the status is that the candidates for all these mock modular forms have been proposed for all conjugate classes of M24. And actually, I won't bore you with all the checks that have been done. Let me just say it. You can try to construct explicitly the representation. You can try to check with what we know from geometry. You can twist this diagram, check for its internal consistency. And the reason why I'm talking here is that all the checks have been passed. So let me just summarize by saying that, well, we don't understand why M24 is there in string theory on K3, but we're pretty sure that it's there. Okay, so the challenge here is actually to understand the stringy K3 geometry, because these results are clearly evidence for some stringy symmetries that we don't understand yet. And we can also point out that it's important to do so, because K3 shows up everywhere. And we can also observe that unlike the previous moonshine, this moonshine has more interesting physics. We have never seen black holes, wall crossing, and all that in the older versions of moonshine. So that summarizes the first part of my talk. And let me go to the second part. Well, in my introduction, I didn't tell you anything about this part except for that we have a puzzle and we think we can solve it. So what is a puzzle? This puzzle, again, has a long history. It started with this strange question, and I apologize for the typo. So actually, it says, for every positive integer n, we can define a certain subgroup. I call it the gamma 0 n plus. Its precise definition is not so important, but it's a certain discrete subgroup of SO2R. And you might or might not want to ask this question: what are the prime numbers P such that these groups, gamma 0 P plus, have genus 0 fundamental domain? Okay, this is certainly an unanswerable question. And the answer is, okay, you just get a set of prime numbers. But what is very funny is that this set of prime numbers is the same set of prime numbers that divides the number of elements of the monster group. And the number of the elements is huge. It's like 10 to the 54. So this can hardly be a coincidence. And that is why that in 73, the mathematician Og has proposed that anyone who can answer this question will get a bottle of Jack Daniel from him. Okay. So a sort of explanation to this puzzle has been provided in the meantime by the Monstrous Moonshine. Why is that? Well, we have observed that J function has something to do with monster. Specifically, it is actually the partition function of a CFT with monster symmetry. Then, as before, we can twist the partition function. And the actual famous Moonshine conjecture says that these partition functions are always modular under certain groups, and all these groups have genus 0 fundamental domain. So that sort of explains the relation between genus 0 and monster group. So that has become sort of like the golden rule of the moonshine business. So these groups are actually very rare among all possible discrete subgroups. But only genus 0 groups seem to appear, and not only in the original version, but in all kinds of extensions. But we still don't understand why, but it seems to be the case. And so after the new moonshine had been proposed, me and my mathematician friend John Duncan one day decided that we're going to check the genus 0 property, just for the fun of it. And what we had in mind was that we would just compute, the invariance group, and after properly massaging it, we would get a list of genus 0 groups. Okay, but life is not so simple. There's just, no matter how we massage our forms, we never get a list with 0, 0, 0, 0, 0. So what is going on? Well, okay. So if you break a pattern, it doesn't feel very good, and you want to replace it with a new pattern that presumably explains both the exception and the old pattern. And if you're lucky, you can also try to find a reason why the pattern should be there. And our inspiration will be ADS-CFD, since, well, as a modern string theorist, if you have a CFD-related question you cannot solve, you just try your luck in the ADS side. So that's what we do. So let's recall some facts about ADS3 CFD2. So in Euclidean 3D gravity, the only smooth solution with asymptotically ADS torus boundary condition is the solid torus. But it doesn't mean that there's only one set of points, because you can fill in the solid torus in different ways. And if you choose, for instance, the contractible cycle to be the spatial circle, then you get what you call the ADS3. If you choose it to be the thermal circle, then you get the BPZ black hole. So that means the set of point of a gravity path integral should be labeled by the contractible cycles, which is basically the same set as elements of SO2Z, but with the subtlety that you have to mod out by elements that don't change the contractible cycle, but only change the non-contractible cycle. That's why you end up with this coset. Okay, so that's the situation for partition functions. And if we want to twist the partition function, as we really like to do these days, and you expect that the boundary condition will again break this pattern and give you some other group. So that's the picture. So now, if you assume the CFTs that you're dealing with, or some higher central charge version of it, to be more precise, has a semi-classical-like ADS dual, then you might want to conclude that your partition function, ZG of tau, can also be computed from the gravity side, and it will look like this, like a summing over set of points. And this kind of consideration has been useful in the so-called fairy tale business. But there we never do the twisting, so we're always talking about SO2Z. That's the difference. So we would adopt this property as the property for it to be Rademacher-Summable. So what does it mean? Okay, so naively, if you want to have something that is invariant under a group, then you can just write down any function you like and summing over its images. And explicitly, you'll get something that is invariant. But life is usually not so simple, because usually the sum diverges, and you need to regularize it. And the regularization will usually, more often than not, introduce some anomaly that spoils the group you started with. So, for instance, so the Rademacher-Summability, we would define it as the existence of such a sum expression that is convergent and anomaly-free. So the resulting sum will still be invariant under the group. A famous example would be our old friend J function. Well, the detail of regularization will not be important, but just note that it can be written as a sum over the images of just something, as simple as you can possibly have q to the -1. And that's why it's called Rademacher sum. And it turns out that this property puts very stringent constraints on the possible groups that you can have. For instance, if you're interested in having a modular function, or weight 0 in technical terms, and then this condition will be the same as the condition that the group you're summing over has to have genus 0 fundamental domain. Okay, there's some way to understand this intuitively, but I won't have time to talk about it. And in particular, all the modular functions that appear in Monstrous Moonshine are basically the regularized sum of the same term, q to the -1. You just have to change the group a little bit. And so that's the Rademacher-Summability. And here, recall that we're dealing with something else. We're dealing with something a little bit more subtle, which is called a weight-half Mach modular form. And in this case, actually, the two conditions basically decouple. They have nothing to do with each other. So instead, we just explicitly checked and compute, and such that all the Mach modular forms appeared in M24 Moonshine can be written as a Rademacher sum of the very same kind that appeared in Monstrous Moonshine. You just change the power from q to the -1 to 1/8. So, to summarize, we now propose a new pattern, a new rule that is the Rademacher-Summability. And in the old cases, where the CFT spits out modular functions for you, this property is the same as genus 0 property. And in the new cases that the CFT spits out Mach modular forms, the genus 0 is no longer relevant for Rademacher-Summability. And we explicitly verified that this is the case. And the motivation for proposing such a new pattern can be motivated by ADS-CFT considerations. So, maybe a physicist deserves a small glass of whiskey. And we have seen that there are many applications of ADS-CFT to many things. So maybe we can start thinking about its application to more mathematical side of string theory. And with this, I'll end my talk.
Yeah, thanks a lot for your nice talk. Again, time for questions.
When you twisted the partition function, does it amount to orbifolding the K3? So in the sense like you have to count twisted and non-twisted sectors?
Well, that's after almost, but it's one S duality away. If you exchange the two, put the G insertion on the other cycle of the torus, then it's like what you said. So basically, there's a whole new story there under the name generalized Moonshine when you do exactly that, and it will give you another set of objects.
Thanks.
What you're proposing at the end is that the K3 conformal field theory has an ADS3 dual?
Well, or the higher central charge version of it, that would be more plausible.
What do you mean by the higher central charge version?
For instance, if you take the symmetric products of K3 and then put the sigma model on it, and we know that alas Schrödinger-Waffa should be dual to ADS3 times S3 times K3, with the K3, it was the ADS radius controlled by the central charge.
So why doesn't that tell us that the summability had to work, in a sense?
Yes, exactly. So I have actually one slide on this. So for the M24 case, it's pretty clear that it has to work. Although there's some subtlety, like exactly, what kind of condition does this duo have to have in order for the saddle point approximation to make sense. That is something that I'm thinking about, and it's not immediately clear to me under exactly what condition the saddle points have to work.
Are there more questions?
I have two questions about the first part of your talk, the twisted elliptic genera. First question is, what is the physical reason that makes twisted elliptic genus Mach modular? And the second related question is, Mach modular forms come with small baby examples of simpler modular forms, namely for each Mach modular form you can associate the shadow.
Okay.
Yeah, is there a physical meaning to the shadow as well?
Yes. The two questions are closely related. This first question is how you get that Mach modular form is by decomposing the elliptic genus, which is a nicely modular thing, into contributions from different multiplets of n equals 4 superconformal algebra. And the BPS, well, the massless multiplets has like characters with slightly screwed up modular properties because the multiplet is short. And those are actually given by the famous Lurch sum. So if you subtract those, and the two shadows have to cancel. So then, the rest, the massive part is also Mach modular. So that's the first question. And the second question is, yes, the meaning of the shadow is just that the shadow has to be the same as the shadow of the upper Lurch sum. And the upper Lurch sum has exactly that shadow. And why we have an upper Lurch sum is just because the n equals 4 multiplets give us that.
One more question.
I guess I have two questions. One question is, you described this property of the twisted K3 elliptic genus, but you also argue that 1 over 8 to the 24th counts half BPS states, and you can decompose that into M24 representations by taking the representations of S24. So if you twist that by elements of M24, do you get something with similar properties?
Yeah, I mean, I'm not sure what you mean by similar properties, but let me...
Well, I mean, Rademacher-Summable or whatever the criteria is.
Oh, yes. I think, yes. If I understand correctly, the answer is yes. And the second comment, and the comment I want to make is, if I understand correctly, Samir Murthy and Atish Dabokar are working on deriving those Rademacher sums from first principle from the gravity side. Well, not the twisted one, but at least the original one.
Okay. Could I ask just one more quick question? So
Yeah.
in that 1 over 8 to the 24th, that's counting the total number of BPS states, but those BPS states transform, in that sum, transform under different representations of the rotation group, the little group of massive particles. So if those things are transformed by M24, M24 can't commute with the rotation group. So what's the total group of the symmetries, or is that evidence that M24 doesn't actually act on the BPS states?
Yeah, that's a good question. And yes, and you raised the question or similar question before, and I still don't have an answer to that. So I think we should discuss more next week when we're in Zurich.
Are there more questions? No, if not, let us thank Miranda again.